So in this section of aqueous reactions, we will talk about redox reactions only. One little portion. It's not as little, but anyhow. Okay, so you've already learned about the different types of reactions, the synthesis, the double displacement, single displacement, decomposition. There is a reason why I'm bringing this up, okay? Because when we talk about reactions, we still need to know what kind of reaction we are talking about, okay, about this classification, which again, remember, it's kind of how the atoms are being rearranged, all right, because the other classification of the reactions is precipitation reactions, neutralizations, and then the oxidation reduction. So we've covered the precipitation and neutralization in another section. So in this one, we are focusing only on oxidation and reduction, all right? So which is also called redox for short. So redox is oxidation and reduction. So to understand that, we first need to understand what is oxidation and what is reduction. So oxidation in general, if you want to look at it from the elemental point of view, is addition of oxygen, and reduction is removal of oxygen, whereas reduction would be addition of hydrogen and oxidation is removal of hydrogen. Now these two you can do only if you have oxygen and hydrogen in the reaction. If you don't, then how do you do it? By electrons. So loss of electrons is oxidation, gain of electrons is reduction. So Leo and Ger, and I'm not that much into mnemonics, not because I'm not into it, because I don't know very many, but this one I do. Okay, so Leo, Ger, all right, loss of electrons, oxidation, gain of electrons is Ger, which is reduction. Generally, metals will lose electrons. You know that already. Non-metals will gain electrons. So one other thing that we talk about in oxidation reduction reactions is what is an oxidizing agent and what is a reducing agent. A reducing agent is something that causes something else to reduce. So it itself will get oxidized. So I know it's a little confusing. So I'll give you time to read it, okay, afterwards, but I just want to say one thing. Reducing agent is something that causes something else to reduce, which means something else to gain electrons, which means it itself is getting oxidized, which is metals. So the way I remember it is that reducing agents are metals. Oxidizing agents, on the other hand, are the non-metals, because oxidizing agent cause oxidation of something else, which means they cause something else to give electrons. Okay, so generally the non-metals will like to take electrons. Okay, and so therefore they are called the oxidizing agents. So how do we write redox equations? So here's a simple example, okay, very simple one, and you might have done this in the lab also, is where you take zinc and copper, and you can take magnesium here instead of copper, it doesn't matter, but you take zinc and copper. Copper is in solution state, zinc is solid, okay, over here. And over the time, what happens is that zinc becomes zinc 2 plus, okay, which means that zinc is actually becoming aqueous. So this is not dissolving in water, by the way. There is some reaction going on. Okay, dissolving would mean a physical change, not a physical change. This is something chemical happening. And then copper is copper 2 plus is coming out of the solution as copper, and that's kind of what is shown over here. So zinc is this rod, and then this is copper solution, which is generally blue, but copper as a precipitate by itself is actually a little reddish. Okay, and so this is kind of shown here. So over the time, this is what happens. So what's going on here? Okay, and what's going on is that zinc is becoming zinc 2 plus, so it's going into solution, which means that it is losing 2 electrons, so it is oxidizing. We can say oxidation is occurring. On the other hand, copper is gaining 2 electrons, and therefore it is reduction. All right, so this is the process that's happening. Again, this is not just zinc dissolving in solution. That's not what's happening. Zinc is actually losing electrons and therefore going from zinc to zinc 2 plus. It's a chemical change, okay, that's happening in here. So this is kind of how we follow things electronically. Okay, here is another example, and this is for magnesium reacting with oxygen. So When it reacts, it gives magnesium oxide. Okay, so what's happening here? Now you can classify this kind of a reaction with just by oxygen, right? Remember, so we talked about the definitions of oxidation reduction. Oxidation is addition of oxygen. So here magnesium is adding on oxygen, so it is getting oxidized. All right, so what is getting reduced then? Oxygen is getting reduced. By the way, so just so you know, redox reactions go hand in hand. Okay, it's not like that you will just do oxidation and not do reduction in a reaction. Okay, that doesn't happen. If something is getting oxidized, something is getting reduced, which is why we use the term redox, because this is something that happens, okay, all the time. It's not about all the time, it's about the fact that they happen simultaneously. Okay, if something is getting oxidized, something has to get reduced. All right, so in one reaction you will see both. So for example, in the zinc and copper, this was happening, okay, at the same time. So here also it's happening at the same time. So here magnesium is getting oxidized, so it means oxygen then must be getting reduced. All right, so if you know one chemical that is getting oxidized, then you know the other one must be getting reduced. Okay, you don't have to have too much debate with yourself about this. So this is all great because you can tell with oxygen, but then how can you do this with electrons? Okay, so can you do this with electrons? You can, absolutely. Any equation you can figure out what is losing electrons, what's gaining electrons, but you need to figure that out in order to figure out the oxidation reduction with electrons. To do that, you need to find what is called oxidation numbers. Oxidation number is what is called like a valency or a charge, okay, on any element. That valency or charge can be minus or plus. It could be +7, +4, -4, whatever it is, but it's an oxidation number. It's just called oxidation number. There's nothing like a reduction number, okay? So it's called an oxidation number, and elements have it, and you can calculate it. Okay, so it's not like a hard calculation, by the way, don't be scared. You don't need your calculators, but it is something you can figure out. Okay, so we can do that for magnesium and oxygen also. Okay, so but you need to learn the rules for finding out those oxidation numbers. Okay, so in the next slide we actually have those rules for you. So elements, for example, will always be 0 in their native state. Okay, so magnesium, for example, in the previous slide would be 0. Okay, sodium would be 0. All the diatomic gases would be 0, 0, 0. Okay, so group 8 we're not even talking about, but if we were, group 8 also would be 0, okay, to begin with. So all of these in their native states, in their normal elemental state, these are all considered to be 0. They don't have any charge on them. Okay, if you have any monoatomic ions, what does that mean? It means that any single atom, okay, so sodium here is a single atom, whatever charge is on it is going to be the charge on it. Okay, so sodium is +1, magnesium 2+ is 2+. Okay, so what we mean by monoatomic, if you keep that in mind, is that it should be this and not this. This is not monoatomic. Neither is this. This is not monoatomic. Okay, these are two sodium ions. So keep things different. Okay, don't mix and match things like that. So this is a sodium ion. This would be a diatomic, right? Because that's how we deal with diatomic. So this would be a diatomic sodium too. But that, I mean, that doesn't even exist. But I'm just saying, okay, just to tell you. So if you have a monoatomic ion, then whatever the charge is, that's the charge, okay, on that element. Oxygen is generally going to be -2. By the way, the monoatomic ions here, just one more thing about monoatomic ions, is that whatever group they belong to, we did this in, before with nomenclature also, is whatever group they belong to is the charge on it, right? So group 1 was +1, group 2 was +2, group 3 was +3, group 7 was -1, group 6 was -2, and group 5 is -3, which was the nitrogen group, right? So all of those ions, they are set, okay? You don't have to worry about those. We will worry about them, but in a different way, okay? So those are pretty much set, especially group 1 and group 2, +1, +2, set. Oxygen is supposed to be -2 all the time. Okay, so generally when we start calculating oxidation numbers, we use oxygen as a starting point and it's always -2, only except when it's in hydrogen peroxide. Okay, other than that, it's always going to be -2. And if I remember, I will try and do the calculation here for you later on. Okay, what the oxidation number of oxygen is. It's -1, but how do we get that? Okay, I'll do that for you. Other than that, oxygen is always -2. Hydrogen, which is on the left hand side in group 1 is supposed to be +1, but hydrogen can always also be -1. Okay, so when it combines with metals, then it's going to be -1. Always remember, when you have a compound, whatever is on the left hand side is positive, whatever is on the right hand side is negative. Okay, when we learn naming of compounds, when we start learning how to write compounds also, we always write positive first and then negative. Okay, so positive and then negative. So positive cation is always written first, anion is second. Okay, that's your big clue as to what should be the oxidation number. Should it be positive or should it be negative? Okay, so when you have hydrogen, as in HCl, it's positive, but when you have NaH, now hydrogen is negative. Okay, because here this is first, so it's positive, but now hydrogen is second, so it's negative. Yeah, so this is negative and this is positive. All right, that's how it works out. Halogens are always going to be -1, so halogens are group number 7, but the only reason I'm talking about halogens is halogens can actually be in the middle also. So the example I've given you here is HClO3, and HClO3 in Cl is in the middle. If it's HCl like this, then Cl is always going to be -1. But if you find any of the halogens in the middle, then it's different. Okay, then it's going to have a different oxidation number. It cannot be -1 at that point. So we will learn about bonding, and we will learn later on as to why that happens. Okay, as to why is it that chlorine is in the middle. So we'll talk about that. Okay, but otherwise, just remember that for now is just focus on calculating the oxidation number and don't worry about why it's in the middle. The last thing I want to mention is that when you have compounds versus ions, so when you have a compound like HCl, that's a neutral compound. Okay, so which means that the total of the oxidation numbers should be equal to 0. When you have an ion, for example, sulfate, which is SO4, and the charge is 2-, so when you add up for sulfur and oxygen, your total oxidation numbers should lead to -2 because -2 is left over, okay, in there. So just keep that in mind, and as we do examples, I will go over that as well. Okay, so these are your rules for assigning oxidation number. These are the important ones: 0, 0, -2, +1, -1, and then -1 or calculated one. Okay, and all that. Okay, so here is a table of all the oxidation numbers possible, and this is not for you to memorize because there's no point in this. You can't memorize all the oxidation numbers of nitrogen or chlorine. It's not possible. Okay, so, and transition metals, forget it. Okay, you just cannot do that because it's just too many. So you just calculate them. Okay, I'm just telling you over here is that all these oxidation numbers are possible. Okay, but if you look at group number 1 and 2, look at this, except for hydrogen. Okay, and I always said hydrogen is a different little thing. Group 1, group 2 is standard, +1, +2. That's it, it's never going to change. Okay, aluminum, boron, +3, it's not going to change. All right, all of these are pretty standard. It changes over here. Okay, at the bottom it will change, but otherwise it's pretty standard. And then, you know, and as you get to non-metals, then things start changing a little bit. Okay, so you have to calculate at that point. So here is a problem. Okay, assign the oxidation numbers for all the elements in the compounds below. So the first one is magnesium bromide, and then it's potassium permanganate. Okay, so let's take magnesium bromide first. Magnesium bromide, magnesium is a main group element, and so is bromine, so we don't have much to worry about. And I just wanted to do this example to show you that you really should not be stressing out too much, because magnesium is in group 2, so it should be +2, and bromine is in group number 7, so it should be -1. And since you have 2 of those, the total charge is -2. Okay, Why are we calculating the total charge? Because we want to make sure that the total charge should be 0, because magnesium bromide is a neutral compound. The individual oxidation number is actually -1. Okay, that's what it should be. So I'm going to specify here eventually when I write this, okay, that it should be -1, not -2. -2 is not the charge on bromine. The -2 is the total charge, okay, on bromine. Okay, so then let's look at potassium permanganate. So potassium permanganate, what I've done here is I've kind of broke this out in a sort of a table here for you. And we'll do a little bit of an algebra kind of an equation, and you will see it's very easy to do then, okay? Very easy to figure out the oxidation numbers. So we have K, Mn, and then we have 4 oxygens, okay, over here. All should be equal to 0, which means because this is a neutral molecule, the charge should be 0, okay, at the end. So let's do X, Y, and Z over here. So you have 1 atom of X and 1 atom of Y, but you have 4 of Z, which is 4 of oxygen. So potassium is a main group element. You're not going to debate about this one, so that's going to be +1, okay? So you can just look on the periodic table. Manganese, we don't know, because manganese is a transition metal, so we don't know about this. Oxygen, we definitely know it's going to be -2, okay? So the oxidation number on oxygen is -2. Now, the 4 over here indicates that you have 4 of oxygen, so the total charge on oxygen is -8. So the total charge on potassium is +1. The total charge we don't know for manganese, and that's what we're trying to calculate here. And then the total charge on oxygen is -8. So all of this should be equal to 0. So just do the math here. -8 and +1 plus what will give you 0, and +7 then will give you 0. So +1 plus 7 -8 will give you a 0. So which means the oxidation number of manganese is +7. Okay, so go with whatever the main group elements are first. Transition metals you will always have to calculate, okay, pretty much, because transition metals we don't know. Sometimes the non-metals also we don't know, okay, so we have to calculate those. But the oxygen you will always know, halides you will always know. Okay, so here we're going to be dealing with ions now. So assign the oxidation numbers for the elements underlined in the ions below. So now we're not working for oxygen. Okay, I mean, like, we are working to find for oxygen, but not like, you know, we already know what the oxidation number for oxygen is. So we are finding for chlorine and then chromium in dichromate here. Okay, so ClO2 minus. So again, I'm going to split this up. So you have 1 Cl and 2 oxygens, and all the total charge should be -1 on this because the charge is -1. So again, X plus now 2Y, because Y is the oxygen, equal to -1. So I think you know where I'm going with this, right? So X we don't know. Oxygen is -2. We have 2 of those. So that's equal to -1. So X plus and then -4 is equal to -1. So what should X be? X should be +3, because when you add these 2 up, you get -1. Okay, so that's the oxidation number for chlorine. It is +3. So you can see that you don't really have to set up all of this, because I'm just doing this to show you how it is done. But otherwise, once you get good at this, you can do this in your head, hopefully. Okay, but if you can't, that's okay. Just write it out. Okay, always write it out. I still write things out. Okay, trust me, because sometimes you don't really want to make a mistake. Okay, you want to make sure you get it right. Okay. All right, so Cr2O7. So now we have 2 Cr, so 2 Cr, and then we have 7 oxygen, so 7 oxygen. All of this should be equal to -2. So we don't know chromium, right? That's what we're trying to find out. So that's 2X, and then we have the 7 and then -2 for oxygen. Okay, so that should be equal to -2. 2X plus, and then -14 is equal to -2. Okay, so which means what? So 2X then must be equal to +12, right? +12 minus 14 is equal to -2. So 2X is equal to 12. So X is equal to 12 divided by the 2 to give you +6. All right, so oxidation number is +6. So this is for ions. In the cases of ions, you have some charge left over because these are not neutral substances. Okay, and so you have to kind of make sure you do the math correct in order to have the charge left over. Okay, so let's look at this problem here. So it says identify what is getting oxidized and reduced in the following reactions. So we have the first one and then we have a second one. Okay, so in order to figure out for reactions, you need to calculate the oxidation numbers, okay, for all the elements. There's nothing else you can do. So let's look at the first reaction, which is iron 3 iodide and magnesium and iron and magnesium iodide. So to calculate the oxidation number for iron, you need to know what is for iodide. Iodide is -1. Why? Because it's group 7. It's always going to be -1. So if you have 3 of those, then iron must be then +3. Okay, magnesium by itself is 0. And then looking at the product side, iron is 0 because it's an elemental state. And then on the product side here with the magnesium iodide, iodide again is -1. That hasn't changed. And magnesium you don't have to calculate because magnesium is in group number 2. So magnesium should be +2. Okay, so now let's see what's going on with all of this is that you have iron going from +3 to 0, which means that it has gained electrons. So if it gained electrons, that is going to be reduction. Magnesium went from 0 to +2, which means it lost electrons, so that is oxidation. Okay, and you can see nothing happened to the iodide. Okay, it just stayed at -1, and this happens. Okay, that sometimes reactions are, first of all, reactions also may not be redox reactions, and then some elements don't change, okay, in there, they just remain the same. So what is happening is that iron is getting reduced and magnesium is getting oxidized. Let's look at the next one over here, and the next one here is with, oh, such a big reaction here. Okay, so when you see something like this big, then first of all, don't get overwhelmed. Okay, just try to focus on some things. Okay, so I wrote over here that you should ignore water and sulfuric acid. And why should you do that? Sulfuric acid by itself, if you look at it, sulfate is still sulfate everywhere. Okay, so I'm not going to bother with the sulfate. And H2 is H2 over here. Hydrogen also doesn't really change its oxidation numbers. It's either +1 or -1. And in some cases it does change, but here it doesn't seem to be like, you know, by itself. So if hydrogen was by itself, I would worry about it, but it's not there by itself. So I'm going to just focus on the transition metals. Okay, and the transition metals that we have here are iron, chromium, and then iron here on the right hand side. So we're going to focus on that. Okay, so we have to calculate the oxidation numbers. So oxidation number for iron on the left hand side is for sulfate it is -2, so iron should be then +2, okay, on the left hand side. And then here for chromium, chromium is +6. How it is +6 is you just have to figure out by calculation, and here is a quick calculation. Oxygen is -2, so this is minus, let me get my correct pen over here. This is -14, and then potassium is +2 because I have 2, right, of potassium. So -1, +1 and then +1. So the total charge is +2. So chromium must be then +12. And if that's +12, since I have 2 of those, I'm going to divide that by 2. So that gives me 6. Okay, so chromium is +6, and please make sure that you write the plus or the minus because that's an important thing. Don't just take it for granted. Okay, I always write +6, not just 6. So now let's look at the products, and in the products here is the iron, and iron here is bound to sulfate. And how many sulfates do we have here? We have 3 sulfates, so 3 times -2 is -6. Okay, so which means that iron here total must be +6, but we have 2 of the iron, so divided by 2, so that is then +3. So iron is +3. Okay, and then we have chromium, and chromium again is bound to sulfate, and I'm just going to do it on the right hand side because I don't have room there. So sulfate, again we have 3 sulfates, so 3 times -2 is -6. and then I have 2 chromiums here. So the total charge is +6 divided by 2, so that's +3. Okay, so chromium is also +3, okay, in this case. So now what's happening here? Okay, iron is going from 2 plus to 3 plus. So if it's going from 2 plus to 3 plus, that is loss of electrons. Chromium is going from +6 to +3, and that is a gain of electrons. Okay, so gain of electrons is reduction, and iron is getting oxidized because that is losing electrons. Okay, so that's kind of how you work this out. Again, don't get overwhelmed by looking at the equation. Just go through small processes. Usually for these kind of reactions, focus then on the transition metals. Okay. So I said to you before that I'm writing these reactions again, like the types of different types of reactions, but these are now going to be different types of redox reactions. So you can have many kinds of redox reactions. Okay, so in precipitation reactions, we talk about double displacement, acid base was double displacement. Redox reactions are single displacement reactions. Okay, they can be double displacement also. I haven't given any example here, but they can be. Then there can be decomposition reactions like this. So here you have KClO3, potassium chloride going to give you potassium chloride and oxygen. Can be combination reactions, okay, giving you water, and then combustion reactions. Okay, so now this is easy one, right? Because when you add on oxygen, then it's easy because you can see that carbon is adding on oxygen. See, carbon adding on oxygen is going to be oxidized. Okay, so pretty easy one there to do. This one here, you can say this is also a combustion reaction. We can call it a combination reaction. Okay, so hydrogen is burning in oxygen to give water. You can call that either combination or combustion, whichever you feel like. Okay, so that's how kind of it works. So I think this is a good time for me to show you what I was talking about before with magnesium and oxygen, and show you the oxidation numbers on that. Okay, so magnesium plus oxygen to give you magnesium oxide. When you write these equations and when we balance them out, right? So for example, here we will balance these equations out like this. You can balance the equation, but balancing an equation in redox reactions is very different than balancing reactions normally. Okay, so we can balance this out, but generally for balancing redox equations, you have to actually balance electrons. Okay, so I'm not doing that right now. We will do that another time. Okay, so right now, okay, oxidation numbers. So magnesium on the left hand side is 0. Oxygen here is also 0 because both are in elemental state. Magnesium on the right hand side is +2. Oxygen is -2. So I said magnesium was adding on oxygen, so magnesium was getting oxidized. But now you can clearly see it also. So magnesium is losing electrons, so this is oxidation. And here oxygen is gaining electrons, and so this is reduction. Okay, so you can do it electronically also. Where oxygen is present, you have a choice. Okay, otherwise sometimes, you know, we have to kind of do it electronically also. And actually I like electrons because it's you know, it's thorough. Okay, that's what we should say, it's thorough. So here are some other questions also on chemical classification. So classify these reactions as precipitation, acid base, or redox. So here's the first one, and I think this one doesn't require any answer because I had it in the previous one. So this is a redox, and you can classify it either as combustion or combination, whatever you feel like. Then here is zinc and sulfuric acid, and you can see on the right hand side you have hydrogen displaced out. So if hydrogen is displaced out, then that is a single displacement. Single displacements usually are going to be redox reactions. Okay, and so also you can see it as redox anyway. Zinc has lost electrons. In this case, we see what happening. So we have water here, we have ammonia here, and then we have hydroxide. So it seems more like an acid-base reaction. So that's kind of what it is, and it's a double displacement. The ammonia seems to be getting one hydrogen from here. Okay, so it's kind of a little bit of a, I don't know, clearly, but double displacement sounds about right. Okay, so then here this one's pretty easy, right? Because as soon as you see solid, you're like, yeah, I think I know this one. This is precipitation reactions, right? And in precipitation reactions, usually they're going to be double displacement reactions. Okay, so not much to think about there. So one last thing to mention about anything losing electrons or gaining electrons. We've just been saying, okay, iron losing electron here, zinc is losing electrons here, but how readily do they give their electrons? Okay, because not everybody would like to give their electrons. Remember, non-metals actually like to take electrons. So this is kind of defined by the activity series. Okay, this is something we do in electrochemistry later on, and we figure out how this works. But there are some elements that love to give their electrons, and then some that do not like to give their electrons very much. Okay, like gold, for example, we know, because we wear gold jewelry and whatnot, and gold really does nothing. It's very unreactive, which means it's not getting oxidized, it's not giving its electrons easily. Metals will give electrons, right? So this activity series kind of just tells you a little bit, first of all, what kind of ions they are forming. And the second thing is that what elements actually like to lose electrons readily. Okay, so that way when you're in the lab and when you're trying to do some reactions and you think, oh my God, this thing is not reacting at all, well, you can look at the activity series and say, okay, lead is not going to react because, it's at the kind of bottom of the activity series. Okay, so that's kind of what activity series does. Okay, and this is just like a very small portion of activity series, is a larger one. So we will do that when we get there eventually. Okay. All right, so at the end, of course, they're the keywords, so make sure you know all of these terms as to what these mean. Okay, all right, I'm done.